Hello students. Today we will continue our lecture on P-block elements. This lecture is presented by me, Pranit Ghatak, your chemistry teacher. So let's begin. As you all can see from the heading itself, today we are going to continue our lecture on group 13 elements. In the last class itself, we have discussed about the introduction to P-blocks as well as some physical properties of group 13 elements. Okay, in this class we're gonna discuss about some special character and special topics of group 13 elements. Okay, so let's begin. Here the first topic of the today is oxidation state and inert pair effect. As you know, mainly all of the elements of the same group having the same oxidation states. That is, in the case of alkali metals, that is hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. All of them having a similar oxidation state because all of them having a same group, that is group number 1. That is group number 1. Okay, all of them having the same oxidation state, that is plus 1. But in the case of P block, especially in the case of group 13 elements, so the elements are boron, aluminium, gallium, indium and thallium. So all of among these 5 elements, mainly these 4, that is boron, aluminum, gallium and indium, show plus 3 oxidation state. But this thallium shows mainly plus 1 oxidation state. Okay, and thallium is highly stable in plus 1, not in plus 3. So why this happened? Because in a group, that is all of them having a similar properties. Among a group, all the members of the group should have the same properties, so should have the same oxidation state as alkali metals right here, or alkaline earth metal. But here in the case of group number 13, we can see among the 5 members of the group, only 4 members are plus 3, but only 1 member having a difference. It is having plus 1 oxidation state. So what it is happening? Okay, so oxidation state differ, and it is being clearly shown that in the case of group number 13, as we go down the group of the boron family, that is group number 13, the tendency to form plus 1 oxidation state increases. Okay, so as we go down the group, what happens? The tendency to form plus 1 oxidation state increases, and it can be seen clearly, that is the boron positive, that is B plus, is less stable than B3 plus. Okay, so in the case of boron, plus 3 oxidation state is less stable than plus 1 oxidation state. But it is not true for thallium. Thallium, it is quite opposite. In the case of thallium, what happens? Thallium is the plus 3 oxidation state is highly stable than thallium plus 1 oxidation state. Okay, so this is a concept. This problem can be answered by the concept named inert pair effect. So among the group itself, some elements do not fall into the same oxidation state. That is, in the case of group number 13, thallium shows anomalies, that is some differences. In the case of thallium 3 plus is not so stable, but thallium plus 1 is highly stable. Okay, so why it is happening and what is the root cause of that? So to explain this thing, we need to understand inert pair effect. What is inert pair effect? Okay, so it is not, the inert pair effect is not only applicable for group number 13, it is also being applicable for group number 14 and 15 itself. Okay, so when we see that in the last day itself, I have explained to you, that is the skinning effect. The skinning effect of D and F orbitals are very low. As the skinning effect of D and F orbitals are very low, so they cannot shield properly. As they cannot shield properly, so the atomic radius or atomic size get decreases. atomic radius or atomic size gets decreases because of the pore shielding of DNF orbitals. But this pore shielding of DNF orbitals gets maximum when in the case of 6s orbital. In the case of higher elements, mainly the elements having 6s orbital. Okay, so I can give you a chart. Okay, so in the case of group number 13 elements are boron, aluminum, gallium, indium and thallium. Okay, sorry, indium and thallium. Similarly, in group 14, carbon, silicon, germanium, Sn, Pb. And group 15, nitrogen, phosphorus, arsenic, Sb, bismuth. So among all of these elements of group 13, 14 and 15, what happened? These elements, that is thallium, lead and bismuth, having 6s orbital. The electron configurations having, in the case of thallium having the electron configuration of 6s1, 6s2, 6p1, lead 6s2, 6p2 and bismuth 6s2, 6p3. Okay, so among all of these elements, this thallium, lead and bismuth having 6s orbital in it, and all of them have fully filled 6s orbital, that is 6s2 configuration. Okay, so in what happened, due to the pore shielding of DNF orbitals, the energy gap between the 6s and 6p and 6s is so high, the energy difference is so high that the 6s orbital cannot participate in the bond formation. So actually, due to the pore shielding of DNF orbital, the 6s orbital becomes so deeply seated, and that is why it cannot act as a valence shell, or it cannot contribute to the valence shell configuration or contribute to the bond formation either. So that is why the electrons of the 6s orbital cannot participate in the bond formation. Okay, so in not only for the case of group number 13, it is same for the case of group number 14 and 15 itself, that is for lead and as well as bismuth. Okay, so the electrons of the 6s orbital cannot participate in the bond formation as they are highly deeply seated. Okay, and as they cannot participate in the bond formation, the 6s orbitals, the electrons of 6s orbital, so that is why they will not show any oxidation state. Okay, they will not contribute in the oxidation state. Okay, so that is why in this group what happened, we generally see G-2 oxidation state for the case of thallium, lead as well as bismuth. That is, in the case of group number 13, the thallium should having an oxidation state of +3, but it show G-2, that is 3 minus 2, that is 1. That is 1. Thallium is showing 1. In the case of lead is the last number is 14, so the last number is 4, so the oxidation state should 4. Of lead should be 4, but G-2, that is 4 minus 2, it will be +2. And similarly, in the case of bismuth, it should have an oxidation state of 5, because 15 means last number is 5, so oxidation should be 5, but it is showing G-2, that is 5 minus 2, that is +3. So this is not only true for this concept, is not only valid for group number 13, it is also valid for group number 14 and 15 itself. So this concept is being called as inert pair, because these two electron pairs from the group number 6s2 from the orbital 6s is not being participated in the bond formation. It is being acted as an inert pair, inert electron pair. So this concept is known as inert pair effect. Okay, I hope you have understood this concept. And the other thing is covalent character of group 13 elements. Group 13 elements are quite covalent. Okay, so why they showing the covalent character? Because there are mainly three reasons. That is, the Fajans rule is being applied to it. That is, smaller the cation, higher will be the covalency. In the case of group number 13, the cations are highly smaller. The size is highly smaller. So Fajans rule can be applied, and higher smaller the cation, higher will be the covalency. Okay, so that's point number one. The point number two is their highly electro ionization in high ionization enthalpies or energies. Okay, so as the group number 13 elements have high ionization enthalpies, which makes the formation of ionic compound very hard. Okay, so that is the second reason. Okay, and the last reason is they have relatively higher electronegativities. As they are relatively higher electronegativities, so the electronegative difference is not that much. Okay, as we know that if the electronegative difference is not that great, then it cannot form a ionic bond. Okay, so at least electronegative difference should be at least 1. Okay, but in the case of group number 13, as the electronegativity is so high, that is why the electronegative difference is not that great among the molecules itself, in the atoms itself of the molecules. So that is why the group number 13 elements cannot do a ionic bond. It's rather okay, rather they do a covalent character or covalent bond. Okay, so let's move to the last topic of the day. You may be heard that the boron, although it is a group number 13 elements, it shows some anomalies. So some anomalous character or anomalous behavior as well. Okay, so why boron does show the anomalous character, okay, or anomalous behavior? It can be answered by 3 to 4 points. That is, mainly it has very small size, and that is why it is having a very high ionization energy, because we know ionization energy, or IE, is proportional to charge by radius. As the radius is small, so ionization energy will be high. So that is one reason behind the anomalous behavior of boron, as well as high electronegativity. Due to, I have also been showing that electronegativity also being proportional to charge by radius. As the radius is very small, so electronegativity is also high. As the ionization energy similar to the electronegativity of the boron is also high, very high. And absence of d orbitals in the valence shell also is a potential parameter that decide the anomalous behavior of boron. Okay, so in this class I have explained some characteristics of group 13 elements, that is the inert pair effect and oxidation state, as well as the anomalous behavior of boron, as well as the covalency of group 13 elements. Okay, so I hope you have understood this part very well. If you have any kind of doubt regarding to this class, please ask me in the comment section below. So that's it for now. Thank you very much.